My name's Jared Ram. I'm the cloud security, actually I'm just the security product manager at Rackspace now. So I own all customer-based security products for all Rackspace customers. That's public and private and cloud and dedicated these days. Today we're going to be talking about the state of cryptography in Python, or as we like to term it, a story about people who make bad life decisions. Because for those of you who have worked on crypto in the past, it can be quite difficult. Normally I have a co-speaker, Paul Kerr, who is enjoying himself in San Francisco and ignoring me at the moment. So we're going to proceed without him. So basically, how did we kind of get into this space for us? So I started a project about a year and a half ago now. That sounds like Kevin in the other room.
We need to fix that.
It does sound like Kevin. Anyway, so started a project in OpenStack that we called Barbican. And basically, the reason we started Barbican is we looked across OpenStack, and there were a lot of people in OpenStack that wanted to offer encryption, right? So how many people are familiar with OpenStack first? OK, so about half. So OpenStack's an open source free cloud platform, right? So it allows you to kind of build your own clouds, mostly aimed at building private clouds for folks, but Rackspace's public cloud also runs on top of OpenStack. So we were looking at, you've got cloud servers for compute, you've got storage, and all these various other aspects that you would expect in a cloud like AWS. And a lot of customers wanted, or a lot of developers and product managers stuff wanted to be able to offer encryption. And so to be able to offer encryption, they needed some kind of key management platform, right? So we looked at all of these guys that wanted to offer encryption, and we looked at, here's their diagrams and all this. They're all super complicated and detailed. And in the bottom right-hand corner, there was just this little box that said key manager, right? And we would go and ask them, hey, what's the key manager? And they'd be like, we'll figure that out. Like, OK, but that's actually the hard part, so why don't we go figure that out for you? At the same time, Rackspace was looking to revamp an existing offering that we offer to customers around SSL certificates. So we sell SSL certificates to customers. It's not a huge business for us, but it's something that customers need, obviously, and so we try to make it easier for them. And we wanted to revamp that both to offer some new products, offer it to cloud customers, and there was I wanted to make it more secure from a internal perspective and more isolated and some of those types of things. And so Barbican was kind of born, right? So as we were looking at building Barbican, if you're building it in OpenStack, it needs to be built in Python. So as we started to look at what we were going to need in Python to do this, obviously we were going to need to do a lot of cryptographic operations. And so we started to go investigate, OK, well, where's crypto in Python, right? How capable are we of doing all of this work? Cue our 80s montage, and then we ended up with this, right? So what we wanted out of the process was to find something that had the algorithm support that we wanted. Barbican needs to operate as an open source product across a wide variety of platforms for a wide variety of customers who have a wide variety of needs, right? So we couldn't really be very prescriptive as to what algorithm choices they wanted. Some people want to use some pretty fancy stuff from DJB and a few other things, and that's really nice. Some people are under FIPS requirements, and there's a very specific list of the things that they're allowed to use, and they can't use anything else. So we wanted to be able to support those kind of standard operations and the kind of wider operations. We want it to be open source. Rackspace is a big open source fan. Obviously, OpenStack is open source as well, so it had to be something that could be distributed without too much pain from a licensing perspective. We wanted it to be maintained and tested, so we wanted it to actually have been updated in the last 5 years, be maintained by more than one guy in his spare time, and actually have some tests to kind of prove that it was working and functional. And finally, we wanted to make sure that it supported a wide variety of Pythons. And so we have a lot of folks that run PyPy. In fact, we have some of the core contributors that work for Rackspace. We want to be able to run in Py2 and Py3 and all of the various different environments, depending on what customers wanted to be able to do. And so we wanted to be able to kind of find that stuff. So fundamentally, what we're looking for is a library that we could trust to kind of meet all of these needs for us, right? So one thing we're going to spend a lot of time talking about today is C. Right, and it's an unfortunate side effect. So as a quick grounder for those of you that haven't dealt too much in Python and crypto in general, at the end of the day, almost all actual cryptographic primitives are implemented in C. There is now a big push to implement a bunch of them in Go. Adam Langley and his team at Google did a lot of work on that. Very, very cool stuff. Even Adam is not really recommending that people use it in production yet, although I think he's being a little overly modest there. But anyway, so from an implementation standpoint, there's a lot of very important things that you need to have to be able to implement cryptographic algorithms correctly. And you can't use Python. So One is timing and memory attacks, right? So you can leak information about a cryptographic primitive that allows you to do Oracle attacks and various other things to recover key material or data material based on timing or memory access patterns. In Python, you don't have a really strong correlation or really strong control over how memory is being used, when it's being returned, and some of these types of things, right? So those kind of constant algorithms matter a lot. All good crypto is already written in C, and writing good crypto is really, really, really difficult. And so we didn't want to do it. So you're pretty much always going to be using these base C libraries, right? OpenSSL has its problems. We've all seen lots of them recently. The fundamental pieces of OpenSSL, the crypto basics, haven't really changed in 10 years and are pretty rock solid. The constructs on top of it, like TLS and various other things, tend to be where the problems crop up. But the basic implementations are pretty well done and pretty trusted at this point. Obviously, a lot of these C libraries have been around for a long time, so they've had actual reviews done by cryptographers. Those things are very expensive to do, so making use of that is very helpful. And like I said, there's some future opportunities around Go and Rust of being able to actually have kind of some modern languages to implement cryptographic primitives in. Go already has a wide group. There's some work being done in Rust, although Rust is still a little emergent at the moment. But we'll see. Sorry, I keep getting flashes of Kevin. So this is a little hard to read here with the projector, but basically we ended up with this list of, okay, so we need to go look at all these cryptographic libraries in Python. Well, to do that, we actually need to go look at all these cryptographic libraries in C, because everything in Python is going to be built on top of these libraries in C. So if we start looking at those, we've got this list of libraries on the left-hand side. OpenSSL, obviously, is kind of the king of the hill. NSS is another big option. So NSS was the original Mozilla, or original Netscape security group wrote it. And then now Mozilla basically Mozilla maintained it for a while, and now it's over at Red Hat. So there's NACL, which is DJB stuff. Botan, which is a C++ library. Relatively interesting, actually. Botan was one of the few that actually had tests, shockingly enough. Common Crypto, so these is now getting out of the open source world and into Apple for Common Crypto. The Microsoft CSP stuff. libgcrypt, which is surprisingly popular. It was one of the big surprises for us in this was how popular libgcrypt actually was. And it actually comes down to a licensing fight between Debian and the rest of the world. And so a lot of Debian packages use libgcrypt because they don't like OpenSSL. And then finally, we added LibreSSL because it's the new hotness since BSD is running around making fun of OpenSSL on Twitter and ripping out large chunks of it. And so we wanted to add that one. And we kind of graded them across how open source are they, right? Whether they're open source or not. Cross-platform, whether they're maintained or not. How ubiquitous are they? How many machines will actually have them without us having to go through hoops to get them installed? Whether they supported the standard algorithm set, and whether they had FIPS compliance. Right, so you can kind of poke through this if you want. I won't go through all of them. Obviously, OpenSSL kind of wins up at the top from all of that. That was to be expected. But there's some other ones that did really well. NSS does relatively well, although I will say that it's not very ubiquitous, and the maintenance is questionable. When you go and talk to the Red Hat guys, it's kind of like, yeah, like we keep it working. But there's like one guy at Red Hat CMO who works on it, and he's got a lot of other stuff to do, and so it's not really something that seems to be kind of really evolving very much. They mostly keep it because it's FIPS compliant, and they needed to be able to have something that they could distribute that was FIPS compliant. NACL, some really great stuff, but it doesn't support standard algorithms. Botan, like I said, very interesting, not very ubiquitous. Building it is a giant pain, especially in Python. It's not FIPS compliant. The Common Crypto stuff's actually pretty good. Apple's been getting better and better and better at this. They're fixing a lot of bugs in it. In fact, 8 and 8.1 for iOS that just came out fixed a whole bunch of stuff in Common Crypto. In fact, fixed a bunch of bugs that we reported, which was pretty cool. But of course, it's not cross-platform and it's not really open source, although you can go read the source, but it's not open source. Microsoft obviously always has done a good job historically, but it's not on every platform. Gcrypt does a good job, and LibreSSL, so we got a lot of questions about this the last time we did this. Libre is a pretty cool platform, right? Like the BSD guys are known for writing pretty good code in this particular case, and they're doing a lot of good stuff around OpenSSL. They're also doing some stuff that makes it impossible for most people to use it. It's getting more and more cross-platform. That's great. One of the things they did is they went and they ripped out all of the custom ASM code that OpenSSL had written. So LibreSSL at this point is about 20 to 30% slower than OpenSSL at most major cryptographic kind of operations. That basically renders it useless for most actual production scenarios. It's getting better. We'll see. I mean, I think their argument is that over time they'll be able to tune it in various other ways that'll get that speed back. I hope that they are successful in that because, you know, a good maintained C library version of OpenSSL would be really great for everybody. So So we're hoping on that one. We'll see how it goes. And then obviously, since they ripped out all the FIPS stuff, they lost their FIPS compliance. To be honest, I don't care about FIPS anymore. I think it's basically a waste of effort to worry about it. But some companies don't have an option. All right, so you're not gonna be able to read this at all, so I'll have to cover for it. So now that we know what all the C library state was, it was time to go look at how those C libraries map to Python. Cool, finally get to where we want to be. So again, we looked through a whole set of libraries, and we kind of put them by, okay, well, what C backend are they using, right? Because we care about that. Whether they're maintained or not, what versions of Python they support, whether they've ever been reviewed by anybody from a cryptographic standpoint, and then just kind of general completeness. So we looked at M2. These are all the kind of more famous ones. We looked at M2 Crypto, which uses OpenSSL. It'd been dead for a really, really, really long time. Somebody picked it up recently and got it building again, but they're not really working on it. PyCrypto is kind of the most common cryptographic library outside of cryptography, which we'll talk about in a little bit. PyCrypto uses bespoke C on the backend. They wrote their own C backend. That C backend has never been looked at by anybody. So even though it is the most popular in Python, it has never been reviewed from a security perspective. I'm not saying it's good or bad, just said that it hasn't been done. They don't support PyPy right now. There were some things that they didn't support the last time we looked at this, like authenticated ciphers and some of the types of authenticated cipher constructions and some of the things that we wanted. PyOpenSSL is pretty good. It used to just talk to OpenSSL directly. It sits on top of cryptography now. Python NSS, fine, but it's a really thin wrapper around NSS. And then Botan, like I said, was great, but getting it installed was, you can't just pip install it. Like, you have to hand build all this crap. It's a real pain. And so we kind of stay away from that one. I think the main piece that came with most of these is that even if they were in a relatively good state, they're just thin Python wrappers around the C. So to be able to use the Python, you had to understand the C library. It wasn't like you got away from that, right? And all those C libraries have really, really sharp edges. So if you really don't know what you're doing, right, which no one knows what they're doing when you're talking about OpenSSL, right, you will screw it up, right? And even those of us that spend, like the cryptography guys, we spend weeks and months like digging through OpenSSL code, and we still shit every day where it just makes no sense, right? It's really hard to understand how those C libraries work. And so expecting Python people to be able to just use a Python lib that really just wraps the C library just means that you have to understand OpenSSL, which most people don't, and so it breaks. So at the end of that, we came up with the fact that really what we needed was a native Python library, right? And when I mean native, I don't mean that we're going to write all the cryptographic code in Python. I mean that the library needs to feel like Python code, right? Not like C code. And so we wrote cryptography. And so the goal for cryptography was support for modern algorithms. So we wanted to be able to use AES-GCM and some of the new HKDFs and various other things that we wanted out there. We wanted to be able to improve the ability to debug and test the actual libraries. Almost all of the C and Python libraries that we saw had almost no testing. The Python libraries obviously were better, but C basically had none, with the exception of Botan. And the Python libraries were spotty at best. We wanted to have a sane, secure API, basically with the idea, if you use the API, it will do the right thing by default, and you have to work real hard to do the stupid thing, right? And kind of basically take the sharp edges away. There are ways to delve underneath the cover, so if you really know what you're doing and you know that you need a particular thing, you can do that, but the standard way of using all of it is that you just use it and things work the way that you expect them to. We wanted to support PyPy and Python 3. We wanted to have a good chunk of people that were working on this. Almost all of the C libraries and the Python libraries were maintained by one guy in their spare time. And so the level of movement on these libraries was very, very, very slow. We wanted to encourage the use of kind of the newer type of algorithms, get away from some of the stuff that people kind of use by default. Basically, we wanted to build cryptography for humans. And that's what we were kind of aiming at. So we started the PyCA, the Python Cryptographic Authority. This is kind of the organization that we wrap it around. If you go to GitHub/PyCA, has all of the stuff for that we're working on. So as soon as we started cryptography, a whole group of people started to kind of coalesce around people who were interested in security and cryptography and also were interested in Python. And so those were guys who maintained PyOpenSSL and guys who maintained PyNACL and the guys who wrote service identity, which is about hostname verification, and the bcrypt stuff, like library implementation. So a whole bunch of people that were like maintaining all these things as onesies and twosies started to kind of bring them in. And now we had this big group of people that understood Python and cryptography. And now we have 6 or 7 projects, but at least now there's more than one person who can review patches and land things. So we've actually got a reasonable amount of stuff in there. It's made things move a lot faster for all these projects, so that's pretty nice. So the way we structured the library is kind of we split it into 3 parts. We have what we call a bindings layer. This is we chose to use a tool out of the PyPy group that allows us to bind to C, right? And that allows us to we can support all the Pythons. So it's PyPy, Python 2, Python 3 compliant, all that kind of stuff, which is very nice. And so we have a binding layer, and this is very much like C in Python. That's it. So like you can literally crash the Python interpreter with use after free bugs. You can do that in the binding layer. This is stuff that most people will probably never touch, but other libraries use that. So about 6 months or so, PyOpenSSL that used to talk directly to OpenSSL now talks to our binding layer, and the binding layer talks to OpenSSL. And that gave them the ability to support Python 3 and PyPy, which they weren't able to do in the past, right? PyCrypto is actually going to port on top of cryptography relatively soon here. Paramiko, the next major version of Paramiko, will port on top of cryptography pretty soon here. So cryptography is actually, I've got a slide later that has some of the download counts, but it's getting very, very popular. I think we're in the top 200 Python packages now. Anyway, so you got this basic bindings layer. On top of that, we have what we call the hazmat layer. And the reason it's called the hazmat layer is if you don't know what you're doing, do not go in here, right? So these are higher level cryptographic primitives. It's not C level, right? But these are still enough that if you don't know how to correctly put them in place, right? If you don't know how to design the algorithm or design the construct, you will screw it up, right? So there's still very sharp edges in the hazmat layer. Most developers should never touch it. But it is an abstract layer that sits on top of bindings. So a big piece of the library that we'll talk about is we support multiple backends. So it's not just OpenSSL, right? And so the hazmat layer gives you kind of a generic layer that you can say, okay, well, I'm talking about this AES cipher. And that AES cipher will use a different binding layer to map to whatever C library you happen to be using. And then finally, the thing that we hope most people will use is the recipe layer. And recipes are more what you would expect as a developer, right? If you want to encrypt something, there's a box and an unbox call, and that's it, right? It's very, very simple. It's very similar to kind of, if you've ever used Pineapple, it's very similar to some of those types of things. And so the idea is it's a very high-level API that's aimed specifically at solving problems that developers have. I want to protect this data. I want to, hash this or sign this or whatever it is, without having to worry about what algorithms you have to choose or what, worrying about algorithmic agility or how you generate the keys or how you store the keys or how you put the data together and whether you sign before you encrypt or MAC before you sign. You don't have to do any of that stuff, right? So all you need to do is just say, all right, I want to do this, and it's kind of opinionated and it does it for you, right? So right now we support OpenSSL. That's the primary backend on all of our supported platforms. We also have a backend for Common Crypto. So if you're using it on a Mac, it will actually use Common Crypto if you want to do it that way. We also have some work that's being done. It's not done yet on multiple backend that allows you to use multiple backends at the same time. And where that becomes really valuable is if you want to do something like, well, I'm going to use OpenSSL, but I also want to use scrypt. Well, scrypt doesn't exist in OpenSSL. So I want actually 2 C libraries that I'm going to bind at the same time. You just use a single Python library and say, I want to call this and I want to call this. And underneath the covers, we figure out how to make all that stuff bind together for you. And we're looking at any C backend being included. A bunch of C backends are coming over. We'll see how that goes. They're not too hard to bring in, but it takes some time. So a big goal for us was about testing. And so we spent an enormous amount of time and energy, and Rackspace grants an enormous amount of money to the project to be able to run our testing infrastructure so that we could test this library across a wide variety of platforms and OpenSSL versions and OSs and all kinds of stuff. So you can't really read this, but so right now, well, as of LASCON, which was April, we run about 74,000 tests for each run. There are 78 runs per build. So every time that you put in a single PR, there are 78 elements in that build matrix, and each one of those elements is running about 74,000 tests. We run about 15 builds per day right now. It can go up or down, but that's about average. So for each build, we run about 5.8 million tests, and then that works out to about a little over 575 million tests per week. Obviously, so a lot of these tests are based on information that NIST and various other groups publish that say basically if you take this key and this initialization vector and you run this algorithm this number of times, this is the result, right? And they have millions of those. And so you pull them all in and we check them every single time, right? And we run these across, basically how we get this matrix is at the end of the day, we have to run this across a whole bunch of different versions of OpenSSL, a whole bunch of different versions of Linux, a whole bunch of different versions of Windows, a whole bunch of different versions of OS X, right? And so it's all these platforms and they start to multiply and you get this really ugly combinatorial problem where you end up with lots and lots of stuff, right? So Yosemite coming out means that this number has already gone significantly higher. because we had to go build a bunch of new builders on top of our ESX infrastructure to build all this stuff. So there's probably about 30 VMs or so that are involved on the Jenkins side, and then we use Travis to do a lot of stuff as well. Do 45 documentation builds. But anyway, Travis gives us a lot of resources. At this point, we've kind of broken their infrastructure, so I think we're going to have to move off of it. It takes like 18 hours now to run our builds off of Travis, which is kind of not okay anymore. But they've been super cool and donated an enormous amount for us. So that's pretty awesome. So lots of folks here. Alex Gaynor is a core contributor for Python, core contributor for PyPy, core contributor for Django. I don't know what he does with his life other than write Python code. Paul's written the vast majority. He works for Rackspace with all of us. He's busy hanging out in San Francisco and being a hipster. David Reed and a couple other folks, Alex Stapleton. A lot of these guys are Rackers. A lot of them aren't. And then there's about 50 contributors altogether, some of which are pretty active. So we also have a whole group of people that hang out in the channel now that help us with various things that don't necessarily write code, but are actual cryptographers, for example. So like Matt Green will pop in every once in a while and help us with a question if it's like, oh, hey, like, is this construct the right way to build this? Like actual cryptographic questions as opposed to implementation questions. And so sometimes we use cryptography. Currently what we support is ciphers that you could want.
Or like, you know, they actually specifically said
All the stuff that you would want is pretty much there from a symmetric.
Right.
Getting interference from the next room. So. And then all the hashing you would want. So any KDFs KDFs are all in there. Whirlpool, that thing that you basic hashing are pretty much entirely there. Metric support is something we're still actively working on. So like there's a lot of algorithmic support there. There's a lot of functionality. Right now, there's still some stuff around importing various key types and translating those key types between backends. That's kind of active work that's going on now. From a high-level recipe perspective, we support something called Fernet, which is created by the guys at Heroku. And it's a nice boxed format. So if you want to encrypt a piece of data, customer's email address or something that you don't want sitting unencrypted, you basically just kind of tell Fernet, give me a key, go encrypt this data with this key. You go store the key somewhere, and then you just dump this block that it gives you back into your database. And you don't have to worry that underneath the covers, Fernet is doing a lot of stuff for you, right? It's actually inside this block, it's noting what algorithms it's using and what work factors it's using and all these other types. And all those things can be tweaked and changed underneath the covers, and it has algorithmic agility and work agility and all these various other things. But you as a dev don't have to worry about any of that. You just tell it, just box this shit up, right? And it'll do it for you, and you don't have to worry about it. It's pretty nice. So anyway, so you've got kind of big stuff. We just released 0.6 that has a lot more around asymmetric stuff. X509 is currently under major development, and so we should see a good majority of X509 land in 0.7, which should be hopefully here in the next couple of weeks. So we talked a little bit about downstream contributors. So PyOpenSSL is now based on us. So if you're using PyOpenSSL, you're already using cryptography. PyCrypto is in the prototype phase. It'll probably be moved over by the end of the year. Paramiko, that will land the next time they release a new version of Paramiko. The PR is already done. It's just waited. They're waiting to do a point release. Conch, which is the twisted stuff, is probably going to move over as well. So pretty soon, this is pretty much the ballgame for actual cryptographic libraries in use in Python. So once these libraries move over, pretty much every major cryptographic library will sit on top of cryptography. These are kind of download counts. So you can see, like, here's 450,000 a month is about what we pay for. So people are downloading it. I don't know, like our test infrastructure downloads it a lot too, so it could just be all us. But internet points. So we had some questions last time we talked about this about the licensing structure. The project was licensed under Apache 2. There was some concern in a couple of cases that it couldn't be easily distributed in certain scenarios. A big goal for all of us working on cryptography is that you can use it anywhere, anytime, no matter what restrictions you're under from your company or whatever it happens to be. Good crypto should be available for everyone. So we actually had to go back and also license it in BS. So that's in process now. We've had some people that have complained about the fact that we're doing it. I don't know, but it's easy to say. There's this guy named Van Lindbergh who's the chairman of the Python Software Foundation. He's the one who defended the Python trademark when it gets sued and all that kind of stuff. He works for Rackspace. We just dumped this in his lap and he told us what to do. So if you don't like it, you should just go yell at him. He's on Twitter, so you should definitely yell at him as much as possible. We like to give this presentation and not tell him that we're doing it, and then he just gets all these irate people on Twitter yelling at him about 2-clause BSD, and he never understands why. It's really very fun. So anyway, if we go back and look at our original goals, right, did we get what we wanted, right? So
And you just
multi-backend and OpenSSL. It allows us to cover all of the major algorithms that anybody would want, and multi-backend allows us to extend that in whatever direction we want. We're not limited by a single C library having to have everything, right? That being said, multi-backend has turned out to be a lot harder than we thought it was going to be, so it hasn't entirely landed. There are still weird edge cases around what happens when backends have two versions of the same algorithm and what order do you want to load them in. And then, of course, for those of you that have worked in Python, the setup tools morass of nightmare makes it very difficult to actually land a lot of this stuff. So a lot of work going on in there. Open source stuff, it's Apache 2 and BSD. All this code's up on GitHub. You can pull it tomorrow or today. You can pip install it today. Everything works great. If it doesn't work great, then it's a bug and you should hop on IRC and yell at us. It's maintained and tested. Like I said, we have a huge test group. We've got 40 plus contributors at this point, which is really awesome. Adam Langley and some of those guys have pitched in a couple of times. And so it's really starting to get, like, it's not that many people that implement crypto code. So when you have 60 or 70 of them hanging out in an IRC channel, you pretty much got all of them. There's not that many people that are out there. So besides, of course, ignoring the DoD guys and stuff that aren't allowed to come play in the open source world. And then Python support, right now, we actively test on and support 2.6, 2.7, 3.2, 3.3, 3.4, PyPy, and some other stuff as it comes out. So pretty much if you are running Python, you can run this stuff, even if you're running some horribly old version of Red, which is like the bane of my existence. So future work, like I said, X509 is big for us. It's a huge amount of work. Stripe's open source grants stuff that they're doing. I don't know, there's nobody from Stripe here, right? I always ask because I want to thank them. But they basically do grants to open source stuff, kind of Google Summer of Code style. And they did a grant for someone to write a TLS implementation entirely in Python. And so the woman who's working on that, who's Ashfall in IRC, but I don't know her actual name, released a version of it like yesterday. So you can go play with it if you want. It's a full TLS implementation entirely in Python. Probably not something you're going to put in production, but certainly something if you ever want to understand what TLS 1.2 looks like and how it works from a code perspective, it's a hell of a lot easier than reading OpenSSL. But anyway, very cool stuff, and that's helped push cryptography down the road because she needed a lot of features from us, and so we've been doing stuff for her. There's some less common primitives, so Google is super happy about some of the DJB primitives around SHA-SHA-20 and Salsa. So these are new cryptographic primitives that Google is using for TLS. They're pushing a lot of other folks to use them as well, as people have lost faith in NIST and some of the other kind of FIPS requirements. These are really great ciphers. They have, strong resistance against timing attacks and some of the side channel attacks that we've been seeing against a lot of the normal ciphers. They're also quite fast, which is why Google likes them as well. So there's lots and lots of interest in people to be able to start to deploy these things. And then multiple backend support, like I said, we're working on that one. So it's github.com, PYCA cryptography, or you can just go to cryptography.io. We are super anal about our documentation, so it is pretty good. I'm pretty excited about how good it is, to be honest. In fact, one of the major cause of build failures for us is that docs, because we actually check that every link is still live in the documentation before we push it. And the internet sucks more than you would think. So that breaks a lot. But anyway, you can pip install it today. It all works. If you want to come play, I think one of the things that we like to talk about in these presentations is that I run into a lot of developers when they're doing this, and everybody's kind of has the same thing. It's like, well, I don't know anything about crypto. I'm not a crypto developer. And I've been told over and over and over again that I shouldn't implement my own crypto, so I can't really help you or whatever. That's mostly BS, right? I think David Reed, who's one of our wrote that like 20 years of telling developers not to implement cryptography has basically just led to a lot of shitty cryptography. It's the abstinence-only cryptographic approach, right? It's bad. Right? At the end of the day, this is code like anything other, and as developers, you have to use this stuff, and it's becoming more and more prevalent where we will not be able to write systems without having good parts of those systems having crypto primitives and crypto constructions. It's just not going to happen, right? We're going to have to protect more data. Everything's going to be encrypted on the wire, right? You're going to have to be better at this stuff. And so we need developers to come and talk to us, right? If for no other reason, then we need people to tell us when our docs suck. And when we look at the recipe layer is designed to solve problems that devs have, right? Not cryptographic library developers, like application developers, right? And so we need people to come in and say, hey, I'm trying to do this in my app. How do I do this right? And we're like, okay, well, let's go figure that out, right? And then, of course, there's always, like any of the people who work on cryptography, including myself, did not start as crypto people, right? So, Yes, I'm not going to go implement my own version of AES. That's probably not super smart, right? But working with a group of people like this, you can build code, you can get reviews from very, very smart people. It's worth it. So if you have any interest in cryptography, if you have any interest in security, and you want, please come hang out in the IRC channel and help out. There's plenty of stuff to do, even for people who don't consider themselves crypto experts. And I will say the number one way to identify a crypto expert is how vociferously they tell you they are not a cryptography expert, right? Because the more that you work on cryptography, the more you understand that you don't know shit about cryptography. And that's it. So happy to take any questions if anybody has any. Thanks for taking time out of lunch. At the start of this, literally like when this was supposed to start, there were 2 of us. So we were just going to sit down and have a conversation. But they wanted to film it, so I had to get all fancy. So any questions? Yes. It was real bad. That was the biggest surprise. Like I think everybody was super surprised at how little support OpenSSL was getting and the way in which OpenSSL got support, right? So there were like 2.5 guys that worked in OpenSSL. Only one of them did it full time, and they all got paid by feature, right? So they weren't working on it full time. It was like, oh, you're paid to implement this thing on an hourly basis, and so they were just grafting on these ugly bulbs onto the side of OpenSSL, and that's the way it'd been for like 10 years, right? So the thing was just a disaster. Is a disaster. It's still got like VAX support in there. I mean, it's a nightmare, right? And the Python stuff was basically somebody needed something and they hacked this Python library together 8 years ago and they're still stuck maintaining it. And so it's weird to me that like cryptography's only been around for, I guess it's like 8 or 9 months now, but like even 4 or 5 months in, these crypto guys, the library maintainers were coming to us going, please, like I want to rebase my library. I don't want to do this anymore. Like doing this by myself sucks. I didn't want to do it in the first place. It's just nobody else is doing it. And so we didn't run into a lot of problems with people who were really protective of their code bases or any of that kind of stuff. It was really just like, oh, hey, you guys are trying to build a really stable, awesome cryptographic basis for Python. That's awesome, right? And I think, it's funny, like this crew has now gotten to be kind of evangelistic about cryptography. And so like the cryptographic crew are the ones who pushed the PEPs to backport all of the SSL improvements that happened in Python 3 back to 2.7 so that people would get them. And of course, for any of you who have been on the Python dev list, that is an enormous ask to dip into that morass. So anyway, that was the biggest thing that surprised me was just like so many systems, so much critical infrastructure was built on top of this like rickety foundation that no one had spent any time looking at, right? And then Heartbleed and all this kind of stuff started to happen and people were like, oh my God, we should spend money on this stuff. But coming into it, that was the big surprise for me. And of course, just the enormous lack of testing in the C communities. Like most of these C libraries are super old, so you can't really blame them. If they were writing now, they would probably have tests. But like OpenSSL has no testing, like none. Right? They don't actually do a release process. They just like dump some, they're like, here you go. And they have like a sub-point release will change interfaces and break stuff, right? And so there's no kind of actual release, or anything. It's just like 2 guys, and they're like, okay, done, git push, right? And like, here you go, it's the new release of OpenSSL, right? Of course, and then Red Hat makes it even worse because then they take the source and they patch it themselves and don't change the version numbers, and so no one knows what's going on. But anyway, so yeah, that was the thing for me, is just kind of how weird and creepy it was once you got underneath the covers of all this like fancy, so you're running like Ansible and all that stuff. Well, Ansible underneath the covers uses Paramiko, and Paramiko sits on top of all of this crypto stuff underneath, right? And so it's like all this fancy new stuff that we're doing. It's like DevOps and awesome, and then underneath the covers, it's like this really gross stuff that's all sitting on code that was written 15 years ago. So, cool. Any other questions? Yeah.
Aside from the Stripe TLS stuff, what other large portions are written through Python?
Oh, inside us? Pretty much nothing. So Fernet, obviously the construction for Fernet is written in Python. There are a couple of bits that we've done so we tried very hard to stay away from that. The goal being that cryptography should not have to be audited by from a cryptographic perspective. We want to use primitives, all want to be in C. There are some things that we've done. So we have a backend, for example, like we patched OpenSSL to use dev-urandom as a backend instead of OpenSSL's internal like RNG nonsense. That was a really bad idea. So there's a couple of things where we've kind of skirted the edge of something that we should do in Python, but we try very hard not to actually do any of that work in Python. I think the only thing that I would say that would be kind of on the border would be some of the key management aspects of things. So like transferring keys between like OpenSSL and Botan is actually really hard. There's no like agreed upon kind of data structure to be able to do that. And so you end up breaking keys down into the core constituent parts, like their primes, and then you're shipping these primes, and then you have to reconstruct them. So that's a little hinky, but it's not too bad. It's pretty well defined, and then you can do that in Python. It's not really doing a lot of calculation, and it's just kind of moving things around. So it's the goal. We'll see. I mean, like at the end of the day, if this gets really popular, I think, I'd like to get Rack to pony up for us to go and actually have it looked at by a cryptographer. So, or if one of those guys want to do it for free, I'll take that. But those things are super expensive. So. Okay. Any other questions? Yeah.
So for your recipe layer, your recipe layer, as you said, the developers, because you mentioned it's a black box, so the developers put into whatever they want to do.
Yep.
Right. So then, what is the algorithm that layer chose?
So the key piece of Fernet, for example, is as a developer, you shouldn't care. If you want to know, you can go look it up. And if you really want to, you can specify what it is. But the important thing about Fernet is that it has algorithmic agility underneath the covers. And so you can actually change out the algorithm and the work factors and all the other features of what's actually being used from an encryption perspective without having to change your code at all. Right? So imagine somebody finds that there's an attack against AES-128, right? And it's like, oh, well, now I want to move cipher. You can actually just do that on the fly. You tweak a couple of parameters, and now all of a sudden you're using a different graphic primitive underneath the covers, but you don't have to change the rest of your application. But for some users, sometimes you'll have a directive from your security group that says you must use these parameters from an encryption standpoint. You can tune those if you want. Generally, we try to tell developers, don't do that. But if you really have to, then you can. Right? You can delve underneath and kind of say, no, I want this, and I want this, and I want this, and I want this construct with this hash. And so for customers that need FIPS compliance, they have to do that. Because FIPS is very prescriptive about what you're allowed to use. The OpenSSL FIPS module is sliced off, and it only has certain things that you can do and all that. So you have to use those things. But yeah, the goal would be, don't worry about it. It makes a sane default, and those defaults will change over time, but you don't actually care if they change because it handles the change for you, right? So it's one of the things that Matt and I have been talking about for a long time around key management. As consultants, we noticed that a lot of applications would use keys, but they never built the ability to rotate the key. So rotating the key was actually a really painful process. And so you would come in and you would notice that this same key had been used for the last 10 years and they never rotated it. And so, by using Fernet or something like that, it gives you all of that agility and the ability to do all that, but the developer doesn't have to build all of that code and software around it. Fernet just kind of gives you all that for free. Well, not for free, the Heroku guys spent all the money to build it, but it's free and open source. So. If I remember right, you can tweak Fernet without having to dig too deep. It's kind of in the middle. Generally, the goal for us on the recipe layer is to not have anyone say AES, right? When you start talking about algorithms or bit lengths or key generation methods or the different type of random number generations and all that really belongs mostly in Hazmat. But if you really need to reach in and kind of just say, I just want Fernet and 98% of it I'm fine with, but I want to tweak this one thing or these two things, that's probably okay. It's not going to hurt too much. So. Oh, sure. Yeah. It's just Python, right? There's nothing that prevents you from going down to the Hazmat layer other than the name and the fact that we write here be dragons on every single page. So that, yeah. So you can dive down and you can go all the way down to the binding level if you want to tie yourself to OpenSSL and use some method directly. You can do that. The goal is to make cryptography easy to use for devs, and so the documentation kind of drives you to the easy to use pieces of it. That being said, we have a lot of other libraries that sit on top of us, and those libraries need low-level primitives. But the assumption is that those guys know what they're doing, and so that's fine, right? A big piece for us, and it was to Matt's question of what surprised me, right? Nothing worked with PyPy. Nothing when we first looked. Mostly just because how they bound to the C layers was all super old stuff with Swig, and so it just didn't work with PyPy. And so now the binding layer is useful to other library authors, so they just use that directly sometimes. Yeah.
Any more questions? Okay,
All right. Thanks, guys.